Hello, it's Keith here, and this is lesson 47 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at my Mintile series, where we make a multi-platform tilemap that works in the same way on every system, whether they're hardware or bitmap-based tiles. So today we're looking at the Sinclair QL, and we're going to port it. You can see the example code running here today. Now the virtual screen is 256 by 192, which is why we don't go to the top of the screen. And if you're wondering what that weird corruption up there is, that's actually the stack. The stack is currently mapped to a memory area that is actually part of the screen, so we better not write to that area or we'll get a crash. Anyway, Mintile supports moving objects around the screen, simulated bitmaps using the same tile code. And if we figure out what the fire button is and press it, there we go, we can scroll horizontally and our character can flip left and right. The reason we're doing horizontally and not vertically there is it's kind of harder to do horizontally because we have to actually skip some tiles after each line. Scrolling vertically would be far easier because we can just move the starting memory address of the source tile data. So that's why the horizontal example is there. Anyway, the code can also X-flip the sprite, so our character can turn around, and that's being done via a lookup table, which we'll see later. It can't do Y-flip in this version. The reason for that is Mintile was developed for a parody of Street Fighter called Chibi Fighter on the Z80. I didn't need Y-flip, and I thought I was being adventurous enough trying to write this in the first place. What I'm doing is I'm writing a successor to Mintile called Maxtile, which is far more advanced. It supports X-flip, Y-flip, simulated transparency, fast filling of tile, various other things. It's far more advanced, and it's really the successor. This is kind of an early example, if you will, of simulated tile maps on all of these systems. So let's take a look at the code. So this is the file we're looking at today, SQL Mintile. See the Sinclair QL there. And what we're going to look at today is just the code that's related to this tile map. We're not going to look at things like reading the keyboard, moving an object around the screen. That's all been done in the simple series before, and I don't want to have to cover it again. So we're just going to cover the code related to the actual job of drawing the tiles to the screen. Now, when we're wanting to draw things to the screen, everything is a tile map. The background is a tile map. This is the tile map for the background, and you can see that these extra 4 tiles here are the area that can be scrolled into, and if we wanted to scroll vertically, we could just add more down the bottom there. It'd be very easy to scroll vertically, actually. We've got our source bitmap data, the patterns here. These are the tiles, all 8 by 8 pixels. We've got a lookup table there. We'll discuss that in just a moment. Now, when it comes to drawing an object to the screen, the tile map is the background, but our sprites are actually also miniature tile maps. So this is the Chibico character here. That's the character you saw moving around the screen, my mascot for my website. Now, within these tile maps, the tile 0 has a special purpose. Within a sprite, it's a transparent area. For example, if I look at this here, around the feet, there's no tiles, and that's what these zeros are here. So 0 is a tile that's unused. Now, in the sprites, that's just a transparent area, but in the tile map, it's actually an area that has not changed since the last draw. You see, the tile map for the background is actually a cache of changes, and so as the tiles are drawn to the screen, they're reset to 0. Now, basically, the reason for that is that Mintile doesn't use 2 screen buffers. On a system like the Sinclair QL, it's almost impossible. You can do it, but to do so means wiping out all of the system variables. So if you were needing to use disk operations or system calls for some things, that would be impossible. But on other systems, it's completely impossible, specifically the 8-bit ones where memory is just too limited or the hardware physically can't do it. So a decision was made early on when I was developing this to make it use just a single buffer and to try and minimize the changes to the screen so that there was as little flicker as possible. Anyway, when we're drawing the entire tile map, we're basically drawing the entire screen, and so we have this defined symbol screen base, which is the top left corner of the memory for the tile map. Now, the screen memory starts at this address here. That's 2 and then 4 zeros, I think that is, in hexadecimal. And we're adding an offset here. Basically, each 1 pixel tall line is 128 bytes, and we're skipping 32 lines. Reason for that is we aren't using the entire screen. As I said before, we would have a rather bad time if we were using the entire screen because our stack pointer is actually is in the screen memory. I'm not quite sure why that is. I don't know if I did that as a test or something. Maybe I needed to get out of the way for something else, or maybe I was being really aggressive with my testing of my code to make sure if it didn't work, it crashed. I don't know quite why I've done that. Anyway, so the screen base is here. That's for the tile map. When we are drawing the sprites, though, we need to calculate an exact position that our object should start being drawn. all of the tile maps are drawn from left to right, top to bottom in individual strips, and so we only need to calculate the top left corner, and that's what this get screen pos will do. Now this takes an x and y coordinate in D1 and D4, and these are in logical units, which is what I'm using in all of my tutorials now. One logical unit is 2 pixels, pairs of pixels. The reason for that is it works far better with the 8-bit systems to use a single byte for the x and y coordinates, but we need to have an off-screen area for cropping. So by using one unit is 2 pixels, that gives us a croppable area and still only a single byte value. So that's what I've been doing these days. So what we're doing here is we're taking our x and y, we're limiting them to a single byte, and we're then effectively multiplying the y position by 128 times 2. The reason for times 2 is because we want a number of lines, and the D4 is currently in pairs of lines, and 128 is because there's 128 bytes per line. So that's what we're doing there. Now what we're then doing here is we're effectively adding the start of the screen plus the skipped part of the screen, because we're not drawing to the very top of the screen. Our virtual screen is 256 times 192, same as things like the Spectrum for compatibility, and we're then adding that calculation and our x coordinate. And so when we finish this, A6 points to the VRAM address of the top left of the sprite that we're trying to draw. So that's all used by the multi-platform code. The multi-platform code you can see being included here. This is the same on all the 68,000 systems, and I've got some tutorials on how that code works elsewhere. So if you need to see that, please take a look at there. The only part of the code that is platform specific is the joystick reading, which we've covered in the simple series before, and what we're going to cover today, which is the do strip routines. Now do strip will draw a single strip of tiles to the screen. Now if we want to draw an entire screen or a sprite, this is called repeatedly to build the object up, and it's the multi-platform code that calls it. So that's all shared between all the systems. So what does do strip do? Well, the first thing we're doing here is we are loading in a byte from A2 into D0. Now that is the tile number. Now if that tile is 0, then this doesn't want to be drawn to the screen, so we're going to skip over in that case to empty tile. If it's not 0 though, what we do next depends on tile clear. Now if tile clear is set to 1, then we are going to clear this tile. That would be for the background cache. If it's 0, then we're not. That would be for the sprites, because if we clear our sprites, we won't know what to draw next time. So that's why we're doing that there. What we do next is we effectively calculate the offset within the pattern data, the bitmaps for our defined tiles for this tile number. Now D0 is our tile number. There's 32 bytes per pattern, so we're multiplying effectively by 32 there. We are then moving that into A3, and we are adding A5. Now A5 is our source pattern data, so that would be the address of this bitmap data here, so test sprite or test chibi code, depending on if we're drawing our background or our chibi code, because although we're only using 1 byte per tile, we can use different source pattern data for the different tile maps. So our background and our sprites can use different sets of pattern data. So it's not, even though we've only got 1 byte, it's not too bad. Now what we've got at this point is A3 is pointing to our source data, and when do strip is called, A6 points to the VRAM destination. So what we're going to do is we're going to transfer all of the source bytes to the destination. Now after each line we're going to move down a line, and there's 128 bytes per line, so we've got that stored in here. And so what we're going to do is we're going to load in a source byte from A3, our pattern data, incrementing that source, and we're storing that in D0, and then we're moving that to A6, which is our VRAM destination. We're then moving A6, the VRAM destination, down 1 full line by adding 128. This is effectively drawn 1 full line. We've moved along here. That's a 32-bit value. Now on the Sinclair QL, the VRAM layout uses 2 bytes for each 4 pixels, and the first byte contains the green bits and the flashing bits for all 4 pixels, and then the second byte contains the red bits and the blue bits for all 4 pixels. So one 16-bit word is effectively 4 pixels, and so 2 16-bit words, 32 bits, is effectively 1 full 8-pixel line of our tile. So we've moved an entire tile to the screen here, and then we're moving down 1 line. Now we're doing this repeatedly. There's 8 times here, and so this has drawn the entire pattern to the screen. We could have a loop here if we needed to save memory for our code, but the Sinclair QL isn't actually that fast compared to other 68,000 systems. So I've unwrapped this loop, which basically means I've got the commands over and over again rather than lots of looping, and so that saves a little bit of performance. Now once we've got to the end and we've drawn our entire tile to the screen, we want to move back up to the start of the tile, and we want to move across by 1 tile, and that's what we're doing here. We're subtracting the 7 lines we'd previously moved down, we didn't move down on the last line, and then we are subtracting 4 from that value that we are subtracting, effectively moving us across 4 bytes, and that is moving us to the next tile that we want to draw to the screen. So A6 now points to the start of the next tile along. We're then decreasing D7 by 1, that is the count of tiles within this strip, and we're repeating, so that is drawing 1 strip to the screen. Now that's how we draw the unflipped tiles, that draws the entire strip to the screen. What about the flipped tiles? Well, on the Sinclair QL and on most systems, I think the easiest way of flipping the bitmap data is, rather than storing a second copy of all the patterns, is to define a lookup table and flip that lookup data. Now, as I said, the Sinclair QL memory layout basically has 2 bytes for each 4 pixels, and they're in the same configuration. So there are basically 4 bits for green, 4 bits for flashing, 4 bits for red, and 4 bits for blue, and those are for each of the 4 pixels that those 2 bytes actually define. So what we're going to do is we're basically going to take the 2 bits for each pixel separately, and we're going to move them via rotations into the opposite positions, and so that we're basically moving the rightmost bit to the rightmost pixel to the leftmost, the next one along to the opposite position, the next one along to the opposite position, and the leftmost to the rightmost pixel. And we're defining this lookup table. You see, what we're going to do is we're going to calculate all 256 possible source bytes and their flipped equivalent. What we're basically going to do is, we've defined here this lookup table. We repeatedly define it until D1 reaches 255 here. When it goes over 255 to 256, we've defined the entire lookup table. And then the do strip reverse routine, which is the opposite of do strip, this will actually calculate the flipped equivalents, and we're loading the address of the lookup table into A1 here. Now most of the code is basically the same as before. We're reading in our source tile here. We are calculating our offset slightly differently because we are working now in the opposite orientation, drawing across the screen. And what we're going to do is, this time we are going to use a loop because there's more code. It's quite a lot more code to do each line. So what we're doing here is we're loading in our unflipped source bitmap data from A3 into D0 here. We're then using D0 as an offset to our lookup table in A1, and we are storing that result in D0, and then we're writing D0 to the screen and moving across. We're then going to do the second source byte in the same way, and we're going to write that to the screen as well. Now these 2 writes here have done the first 2 parts of the first pair of pixels. So we've done 4 pixels there, but now what we want to do is we want to actually move left across the screen to the second set of 4 pixels on the left hand side. Now we then load in the second pair of bytes from the pattern data, we flip them again with the lookup table, and we write again the results to the screen. Now once we've done that, we're then going to move down 1 line. We're effectively adding this value here, 128 plus 1, to move us down the screen and move us back to the same position to do that draw again. So this is then going to be repeated a total of 8 times. The count is 8, but that debra command will actually run when the D1 is 0. So a value of 7 in D1 will actually run 8 times. So that's what we're doing there. And then what we're doing here is we're moving effectively up 1 full strip of tiles, moving across 1 by subtracting 1020 here. That's what we're doing there. That's moving the VRAM destination, and then we're repeating until we've done all the tiles. So that's how we're drawing our tiles to the screen on the Sinclair QL. Now, as I say, you can go to my website and download the source code, the build scripts for this. Mintile is relatively simple. It's still quite complicated. If you're looking for something really simple, see the Grime 68000 series, which had just a very, very crude sort of character block style drawing of tiles to the screen with nothing clever and no scrolling or anything clever like that. So that's what you want if you want something simpler. If you want to see something more advanced, please wait for my Max Tile series, which will come later on, because as I say, that will do really everything that I imagine is viable on these 8-bit systems at least. I know this is a 16-bit system, but I'm doing the same thing on both platforms, bits for multi-platform compatibility. Anyway, I hope you enjoyed what you've seen today. Thanks for watching, and goodbye.